All right, we have here the predator-prey system from our reading. We have rabbits, which grow exponentially unless there are foxes around, and then there's a negative term on that growth. And we have the foxes, which population does not do well if there aren't rabbits around, but when there's a cross term, then that term can make the growth rate of the foxes positive. So that's our model. What we want to do now is find and classify the equilibrium solutions. So we are looking at x times 3 minus 2y equals 0 for the first equation, and y minus 5 plus 3x equals 0 for the second equation. So we have our two equations, we factored them, set them equal to 0. From this top equation, we can say x equals 0 or y equals 3 halves. So we have two possibilities from the first equation. If we want x prime to be 0, one of these two things has to be true. So let's track through both of those options. If x is 0, we'll plug that into the second equation, and we get y equals 0. So we have a 0-0 equilibrium solution. That makes sense with a population. If there are no rabbits and there are no foxes, then there will continue to be no rabbits and no foxes, right? So that's an equilibrium. And the other possibility was, what if y is 3 halves? So we plug that into the second equation, and we get x must be 5/3. So we have 5/3 comma 3 halves as another equilibrium solution. Now, you got to think these as units of thousands or something. There's no such thing as 1.5 foxes, but we're thinking on a bigger scale here. But this suggests that there is an equilibrium where foxes and rabbits coexist. Is that stable? Is it unstable? If it's stable, then maybe that population can coexist. If it's unstable, then maybe one of the species is going to die out. Maybe they're both going to die out, right? So the next thing we need to look at then is the stability. And for the stability, it's the Jacobian that we care about and that we use for our analysis. And the Jacobian here, the derivative of the first equation with respect to x is 3 minus 2y. And the derivative of the first equation with respect to y is a negative 2x. Derivative of the second equation with respect to x is 3y. And with respect to y is negative 5 plus 3x. So there's our Jacobian. And what we need to do is evaluate the Jacobian at each equilibrium solution. So I'm plugging in 0 for x and 0 for y, first of all. So the Jacobian at 0, 0 looks like 3, 0, 0, and minus 5. I can tell the eigenvalues of this are 3 and minus 5 because it's a diagonal matrix, but if I am not aware of that, then I can just do the trace determinant stuff that we do, and the determinant is negative, so this is a saddle. So we have a saddle at 0, 0. It's an unstable equilibrium. So if there are 0 rabbits and 0 foxes, we will continue to have 0 of each. But if you have a little bit of a rabbit population, then that population will take off, right? So this is an unstable equilibrium. We tend not to return or stay near it if we move away from it. The other equilibrium solution is 5/3 comma 3 halves. We can plug that in as well. So 3 halves for y in here gives us a 0. Let's see, 5/3 for x here gives us a negative 10/3. Let's see, for y, 3 halves, this gives us 9 halves. And 5/3 for x here gives us a 0. So that's our matrix. The trace of this is 0. That puts us on an axis, on the delta axis, on the trace determinant plane. And the determinant here is, let's see, 0 minus something negative. So it's positive. 2 goes into 10 5 times, 3 goes into 9 3 times. This looks like a 15. So we are on the trace determinant plane on the axis above the bottom half plane. So this would be typically a center, but this is from a nonlinear system, so we can't say conclusively that we have a center because we're on a boundary between options. So what we have is either a center, a stable spiral, or an unstable spiral. I remember with the trace determinant plane, we were right here. That means, because what we're dealing with is approximations here, this is a linear approximation, is what the Jacobian is, and the error inherent in the approximation means we're not exactly certain if we get close to this equilibrium solution, if we're on the stable spiral, unstable spiral, or center, and so that's what we have. That's all we can say, is we have one of these three things. Now we will see the phase plane in the reading, and we will see that this actually is a stable center. And the phase plane will look something like this. We have the saddle and the rabbits here. So if there are no foxes and only rabbits, we're on this axis and the rabbit population grows. If there are no rabbits and only foxes, we're on this axis and the fox population decays. So that's the saddle at 0. We don't care about negative populations here, so we're only looking in the first quadrant. And then we have this other equilibrium, and that kind of follows the same arrow directions as a center. And so there are periodic solutions for a center point in the rabbit and the fox populations. And you can see that in the reading, an actual phase portrait with an animation for it. This is the analysis, and that's tying it into the populations and the actual biological question that we have. It's nice to see the math and the interpretation in one place, I hope.